All right, these are the work, power, and energy unit notes. If you divide your notes into parts, they should look something like this, where you have vocabulary. These are our 5 vocabulary words. You have a section for work, a section for power, and a section for example problems. Then on the back of your paper, you'd have energy, energy examples, um, law of conservation of energy, and law of conservation of energy examples. Okay, so this is part 1 notes, and part 1 notes are primarily just about work and power and basic energy. So work is the product of the component of the force exerted on an object in the direction of the displacement and the magnitude of the displacement. Roughly, it's just a force that causes an object to move, creates work. That force and that movement have to be in the same plane with each other. That's roughly what that means. So the formula is work equals F times D. The triangle is there to just mean the change in D. Now, for work to occur, there has to be 3 things that happen. 1, there has to be an applied force. 2, the force has to act through a certain displacement or distance, meaning it has to move. And then 3, the force and a component of the force has to have a component that's on the same plane as the displacement. All right. So if you look at these 3 different pictures, this first one, we're just trying to determine whether work has occurred or not. So there is a force applied. The displacement is 0 though, so there's no work here. Okay, so that would be a no work. Okay, and then there is a force applied. There is a displacement, and they are both horizontal, so this is yes work. Okay, on this one, let me see if I can move things without causing too much of an issue. So we have a force at an angle, so there is an applied force, there is a displacement, and a portion of this is on the same plane, so yes, there is work being done in this one as well. Okay, I'll just do this. All right. So let's read the following statements and determine whether work is done or not. So a teacher applies a force to a wall. Oh my gosh, I'm so tired. And they become exhausted. So, is a force applied? Yes. Did the wall move? No. So, since I'm missing one of my 3, then no displacement occurred, so no work is done. A book falls off the table and free falls to the ground. Well, is there a force applied? Yes, that's weight force. It's going down. Does it move? Yes, it moves down. Are they in the same plane with each other? Yes. So displacement is in the direction of the force, so there is work done. A truck carries a box in its bed 100 meters. So the force actually would be down for weight and up for normal force, and the box is moving side to side. So because yes, there's an applied force, 2, there is a displacement, but 3, those are on different planes. So that would make it no, because the force is upwards on the box, but the displacement is along the ground or horizontal. So since they're not on the same plane, that would be no. You pull your luggage on a cart that makes an angle of 30 degrees for 5 meters. So it goes horizontally 5 meters, and the force has a component that's also horizontal. That would be our f of x. So yes, but it's only in the x plane. So the force that does the work is the component along the ground, which we could find by doing f cosine theta, or our f of x. So work can also be done by saying f cosine theta times d, because that would then make them on the same plane with each other. If the displacement was up and down, then I could have also used f sine theta, because that would have been the up and down force. So you just have to make those 2 match in the plane we're talking about. So the units of work, well, force is in newtons and displacement is in meters. So it would be a newton meter. Well, a newton meter gets to be abbreviated. We could just write it as Nm, but we can go one step further and we can just write it as a joule or a J. Newton meters are joules. Now, if we were talking about the English system, work is actually foot-pounds because the displacement is in feet or foot, and the force is in pounds. So just an FYI on that. So Matt lifts an 80-kilogram barbell upwards for 1 meter at a constant speed. Well, the key here is that he's applying a force upwards, and because it's a constant speed, that means his force downwards has to match. And so if his downward force can be found by the F of G, which we can do mass times gravity, that has to match his applied force up, and he moves it a meter or displacement of a meter. So his force would have to be the weight, which would be mass times gravity. So that would be 800 newtons. And then 800 newtons multiplied by 1 would give me 800 joules to find my work. Okay. Ben carries a 200 Newton suitcase up a flight of stairs. So he is having to apply a 200 Newton force up, and the height is 10 meters. And then he's pushing with 50 newtons of force, and that's at a constant speed. So that's an equal force to the frictional force of the floor. And he's going to do that for 35 meters. So those two are in the same plane with each other. So we're going to have to find this in parts because we want to find how much work he did for the entire thing. So vertically, as he was going up, he lifted with 200 newtons to overcome gravitational force, and he moved a distance of 10 meters. So the work done there is 2,000 joules. And then horizontally, it's 50 newtons and 35 meters. So that gives us, I think, 1,750 joules. So to find the overall work, we would have to add the two together, which would give us 3,750 joules. Okay? So what work is done by a 60 Newton force in dragging a bag a distance of 50 meters? The force is transmitted on a handle that makes a 30-degree angle. So we can find the force by realizing our force is at an angle. We know it's 60 newtons, and we know that we need to look at for components. We know the angle to be 30 degrees. So we can say F cosine theta because we want to find our displacement, which is, notice, horizontal right here. So we have to use the horizontal force. Okay, so we would do F cosine theta times D. So 60 cosine 30 multiplied by 50 would give us an answer of 2,598.08 joules. All right, now power was one of our other vocabulary words. It's the rate at which work is done, and anything that's a rate means it's divided by time. So work divided by time is power, and so the formula for that would just be our capital W divided by T. Well, we know work is in joules and power is in seconds, so joules per second would be our units, but we can also shorten that and create what we call a watt. Okay, so power is done in watts. Now, in the customary unit, power is horsepower. That's what y'all are most likely have heard power done as. Watts y'all hear primarily with electrical power, but it's the same sort of thing. And so about 760 watts, anywhere from, is equivalent almost to a horsepower. Yeah. So what is the man's power in lifting a 3-kilogram object through a vertical distance of 1.6 meters in 10 seconds? Well, we know that power is work divided by time, so the first thing we're going to have to do is find the work. So it also is force times displacement, so we could say it is force times displacement divided by time. So we could say the force would be mass times gravity, because it would be the weight force. And then 1.6 meters is the displacement vertically, and then the time would be 10 seconds. So we would end up with 4.8 watts. All right, so the first part was just about work and power, and hopefully this helps you to complete your homework problems. And if you have questions, please make sure that you ask me during tutorials.